With sextillions of stars populating our observable universe, it's a humbling realization that someday, each and every one of them, including those yet to form, will eventually meet their end. However, the demise of these stars will not be uniform. Depending on their mass and other characteristics, stars can end their lives in a few distinct ways. Some stars, particularly the most massive ones, will end up as black holes. These objects are regions of space where gravity is so strong that not even light can escape. The core of the star collapses under its own gravity, creating a singularity surrounded by an event horizon. Other stars will become neutron stars, which are incredibly dense remnants formed from the collapsed core of a supernova explosion. These stars are composed almost entirely of neutrons and are incredibly compact, with a mass comparable to the Sun but a diameter of only about 20 kilometers. Many stars, especially those similar in size to our Sun, will become white dwarfs. These are the remnants of stars that have exhausted their nuclear fuel and shed their outer layers. White dwarfs are initially very hot but will gradually cool and fade over billions of years, eventually becoming cold, dark black dwarfs. It's a fate that lies far in the future, as the universe is not yet old enough for any black dwarfs to exist. Despite the immense number of stars in the universe and the variety of ways they can end, there are only a few possible end states for these celestial objects. Here's what their fates are, determined largely by their initial mass and the processes they undergo throughout their lifetimes. Look at this. A Chandra image, right, of the Cassiopeia A supernova remnant reveals various elements: iron, blue, sulfur, green, and magnesium, red. Ejected stellar material can radiate heat in the infrared spectrum for tens of thousands of years. The ejecta from supernovae, as illustrated here, can be asymmetric and contain segregated elements. In the right conditions, this uneven material can be irregularly integrated into future generations of stars. At the edge of a star-forming region within the Orion Nebula, evaporating gaseous globules are visible alongside newborn stars, Herbig-Haro objects, and numerous fainter light sources, including protostars, brown dwarfs, and even planetary mass objects. As the gas continues to dissipate, more of these lower mass objects are expected to be unveiled. This ALMA observation of the high-mass protostar cluster G 351.77 to 0.54 has achieved a spatial resolution of approximately 120 astronomical units, equivalent to 0.06 arcseconds at the distance of these protostars. The gaseous material is fragmenting into at least 4 separate cores, suggesting, now supported by further evidence, that core fragmentation plays a crucial role in determining the number of stars that form in these high-mass star-forming regions, rather than disk-related processes. Once nuclear fusion reactions begin within these protostar cores, they will officially become full-fledged stars. Given enough time, every star will eventually die. Stars are born when gaseous matter in space accumulates, fragments, and collapses under its own gravity. This process leads to the formation of dense cores where hydrogen fusion begins, officially marking the birth of a star. The fusion of hydrogen into helium in the core generates outward pressure, counteracting the gravitational forces that would otherwise cause the star to collapse. However, the fate of a star is determined by its mass. The most massive stars, those many times the mass of our Sun, burn through their nuclear fuel very quickly. As they deplete their hydrogen, they begin fusing heavier elements in a series of stages. This process continues until iron accumulates in the core, which cannot release energy through fusion. At this point, the star can no longer support itself against gravitational collapse, leading to a spectacular supernova explosion. Remnant of such a supernova is either a black hole, an object with gravity so strong that not even light can escape, or a neutron star, an incredibly dense object composed almost entirely of neutrons. This cutaway illustration highlights the different regions of the Sun's surface and interior, including the core, the sole site of nuclear fusion. Over time, as hydrogen is depleted, the helium-rich region in the core expands, and the maximum temperature rises, leading to an increase in the Sun's energy output. The equilibrium between the inward pull of gravity and the outward push of radiation pressure determines a star's size and stability. Visible and near-infrared images from Hubble reveal a massive star, approximately 25 times the mass of the Sun, that has vanished without a supernova or other evident cause. The most plausible explanation is direct collapse, a known process by which a black hole can form, alongside supernovae and neutron star mergers. The life cycle of an extremely massive star leads to a Type II, core collapse, supernova event when the core exhausts its nuclear fuel. During the final stages of fusion, typically during silicon burning, iron and iron-like elements are produced in the core shortly before the supernova occurs. The most massive core collapse supernovae usually lead to the formation of black holes, whereas less massive ones result in the creation of neutron stars. Within the innermost regions of a star experiencing a core collapse supernova, a neutron star starts to take shape at the core. Meanwhile, the outer layers collide with it, triggering runaway fusion reactions. This intense process generates neutrons, neutrinos, radiation, and vast amounts of energy, with neutrinos and antineutrinos carrying away the majority of the supernova's energy. The fate of the remnant, whether it becomes a neutron star or a black hole, ultimately hinges on the remaining mass within the core throughout this event. As the Sun transforms into a genuine red giant, swelling to more than 100 times its present size while its core contracts and heats up to ignite helium fusion, the fate of Earth becomes uncertain. While it may be engulfed or swallowed by the expanding solar envelope, it will undoubtedly face unprecedented levels of heat. The Sun's outer layers will expand, yet uncertainties persist regarding the specifics of its evolution and the resulting impact on planetary orbits. While Mercury and Venus are destined to be consumed by the Sun, Earth will teeter on the brink of survival or engulfment. When our Sun depletes its fuel, it will transition into a red giant phase before eventually shedding its outer layers to form a planetary nebula, leaving a white dwarf at its core. The Cat's Eye Nebula serves as a striking example of this potential destiny, characterized by its intricate, layered, and asymmetrical structure, hinting at the presence of a binary companion. At the heart of this nebula, a youthful white dwarf contracts and heats up, reaching temperatures tens of thousands of Kelvin hotter than the surface of the red giant from which it originated. The outer layers of gas primarily consist of hydrogen, which is eventually returned to the interstellar medium as the life cycle of a Sun-like star draws to a close. The simplest and least energy-intensive form of the proton-proton chain generates helium-4 from initial hydrogen fuel. It's essential to observe that helium is only produced from hydrogen through fusion of deuterium and a proton. All other reactions either yield hydrogen or convert helium from other helium isotopes. This sequence of reactions takes place within the cores of all young, hydrogen-rich stars, irrespective of their mass. The energy generated in a star's core encounters substantial amounts of ionized material before it can be emitted at the photosphere. Within the Sun, there exists a vast, non-convective radiative zone encircling the core. However, in stars with lower masses, entire star can undergo convection over periods spanning tens or hundreds of billions of years, allowing red dwarf stars to fully fuse all the hydrogen within them. Red dwarfs lack the capability to fuse elements heavier than hydrogen. Therefore, once all their hydrogen has undergone fusion, they contract into helium-white dwarfs. As an orbiting body traverses the photosphere of a massive star, the star expands in size and significantly intensifies in brightness. However, the ejection of dusty material halts at this point, as it was merely a facet of the pre-merger phase of the astronomical system in question. Stars frequently grow through mergers, transforming into more massive but shorter-lived counterparts. This depiction of a tidal disruption event illustrates what happens when a massive astronomical object ventures too close to a black hole. The intense gravitational forces stretch and compress the object along one axis, tearing it apart and accelerating its matter. The resulting debris is alternately consumed by the black hole or ejected into space. Black holes with accretion disks exhibit significant asymmetry in their characteristics but are far more luminous than inactive black holes lacking such disks. The event horizon of a black hole constitutes a spherical or spheroidal zone from which nothing, including light, can break free. However, outside the event horizon, black holes are projected to emit radiation. Hawking's groundbreaking work in 1974 was the first to unveil this phenomenon, marking arguably his most significant scientific breakthrough. Solar mass black holes are anticipated to decay over a span of 10 to the power of 67 years, with larger black holes persisting for even longer durations. There are two primary methods of generating a Type Ia supernova: the accretion scenario, depicted on the left, and the merger scenario, illustrated on the right. The majority of white dwarfs that undergo supernova explosions fall below the Chandrasekhar mass limit, indicating a strong preference for the merger scenario in most Type Ia supernovae. A precise size and color comparison is shown between a white dwarf, left, Earth reflecting sunlight, middle, and a black dwarf, right. Once white dwarfs have radiated away all their energy, they will eventually transition into black dwarfs. However, the degeneracy pressure exerted by the electrons within both white and black dwarfs will always be sufficient, as long as they do not accumulate excessive mass, to prevent further collapse. Similar mechanism, albeit occurring over longer timescales, is anticipated for neutron stars. Following the demise of the Sun, its residual core will condense to form a white dwarf. Over a span of 100 trillion years, it will gradually diminish, ultimately transforming into a black dwarf. Any planets persisting in orbit around it must withstand gravitational interactions to endure, as gravitational radiation will ultimately lead to their consumption by the black dwarf. Ultimately, only low-mass, isolated stellar remnants, such as lone black dwarfs and neutron stars, will persist indefinitely in the universe. These objects will remain cold and dark, enduring as the eternal remnants of once bright stars. As we contemplate the life and death of stars, we glimpse the vast, dynamic cycles that shape our cosmos. From their fiery births to their quiet, enduring deaths, stars weave the tapestry of the universe. And even in their silence, they tell a story of change, resilience, and the eternal dance of creation and destruction. Thank you for joining us on this cosmic journey. If you enjoyed this exploration, don't forget to like, subscribe, and share. Stay curious, and keep looking up at the stars.